as soon as I put this thing in my pocket. All right. So I'm going to be talking about visual recognition beyond large label training data sets. So if you've been around for the past few years, you know that computer vision systems have made great leaps and bounds. If you take an image like this, you download one of the sort of image classification systems, feed this image to that system, and that system will tell you that this is a partridge. Now, to a layperson, this seems impressive. You know, well, the bird is in some cluttered surroundings. It's even hard to see the boundaries of the bird. And not only is the system telling me that it's a bird, it's telling me that it's a specific kind of bird. It's telling me that it's a partridge. But it starts to sound a lot less impressive when you realize that the system has seen thousands of images of partridges before. If I was given 1,000 partridge images to stare at and then asked to classify that image, I would not have much trouble either. In fact, I would probably do just as well if I saw just a single image of a partridge and was asked to identify. Just to make this point a bit more, here's an animal that you may not have seen before. So this animal is called a Philippine tarsier. How many of you have seen this animal before? Okay, a few. Some knowledgeable people here. For the rest of you, this is your first presentation of a Philippine tarsier. Do you think this is a Philippine tarsier? Okay. Yes, this is a Philippine tarsier. What about this one? Okay. No, this is not a Philippine tarsier. This is a beaver. What about this one? No, this is not a Philippine tarsier. This is a mouse lemur. As you can see, I just showed you a single image of a new animal that you had not seen before. And not only were you able to distinguish it from its faraway cousins, you could also distinguish it from a very closely related species, the mouse lemur. So this is the kind of ability that humans have. We can identify new species from very few examples, even just 1 or 2 training examples. And not only are we able to identify things, animals, etc., we understand a lot more about the image. When I see an image like this, yes, I can tell you this is a tiger in a forest, but I can also draw out the boundaries of this tiger. And I can do that in spite of the fact that no one sat with me and showed me hundreds of images with boundaries of objects drawn in. We want machines to have this ability. This is not just a matter of being, scientifically, this is not just sort of a matter of curiosity, well, how can we make machines more like humans? It's also of practical significance. Collecting annotations is expensive. If I want to build image classification systems, then it's maybe not that expensive. All I need is just a single label per image. But if I now want to draw boxes, I localize where objects are in images, that means I have to collect annotations about bounding boxes, which is harder, which is more expensive. If I now have to segment out images, if I have to mark pixel level labels for images, then collecting that annotation is even more expensive. If I have to build visual reasoning systems that can answer arbitrary natural language queries about images, then I have to get someone to ask these queries, ask intelligent questions, make sure their answers are correct, and so on, which makes things even more expensive. As you can see, building systems that produce deep understanding of images actually is very expensive in terms of annotation. So this is the reason why we want to reduce the amount of annotation. Even if you're not building rich recognition systems, but you're still building image classification systems that just happen to have more number of classes, instead of 1,000 classes, you want to have 10,000 classes or 100,000 classes, it again becomes very, very expensive. So this is the key challenge, the key sort of motive of this talk. We want to build visual recognition systems that require less training data, that require less supervised training data. And the question is, why is this a challenge? This is a challenge because when you have just 1 or 2 examples of a particular category, well, visual concepts have a wide range of variation. They can appear in different backgrounds, in different poses, at different scales, and so on. when you are given just a single example or just one or two examples, it's hard for the visual recognition system to understand, well, what are the different modes of variation that this category can undergo, and how can I recognize this category in spite of those modes of variation? So you might ask, well, this is true. I mean, objects have wide ranges of variation, but so then how are we able to do this? Well, you might think of two possible hypotheses. One, it might be that when a human like me sees an image like this, it might be that I don't think my mental representation of this image is not in terms of pixels, it's in terms of some attributes that are invariant to all these modes of variation. For example, I might look at this image and think of this as, okay, this is a gray colored bird with a long beak and a long neck and some markings on the head. This description is going to be invariant to a lot of the variation, so it's going to help me more in just recognizing this object in its many forms, in its many modes of variation. Alternatively, I can imagine that maybe when I look at this image, I see this image, but I can also imagine what this object looks like in different poses. Like, how will this bird look like when it flies? How will this bird look like if it was floating in a lake or a river? So these two hypotheses correspond to maybe two ways in which we can address this sort of few-shot learning problem, learning from a few examples. We can either address it through learning better representations that are more invariant to the kinds of variations that occur in the image, or we can address it through learning ways of hallucinating new modes of variation, like given a single image, hallucinating how this object will look like from different views or in different poses. And to do all of that, what we would want to leverage is basically our past visual experience. We've seen thousands of animals. Before you saw the Philippine tarsier, you've seen thousands of animals before. So you know the kinds of variations that different animals go through. So that allows you to actually both that can help you figure out both how do I represent an image so that it's invariant to these variations, as well as what should be the what would this new object that I'm seeing look like under all these variations. So the question now is, how do we do few-shot learning by leveraging this past visual experience through these two possible directions? Now, I think the food has arrived, so maybe we should probably do the eating before I actually get into the meat of the talk. Right. Okay, so welcome back. Right, so what we want to do is basically the way humans do things. We want to leverage past visual experience to be able to learn new object categories from very little training data. So the problem setup from that kind of motivation looks like this. Basically, our past visual experience is going to take the form of a massive labeled data set. So let's say we have something like ImageNet, we have labeled, tons of labeled examples for some number of object categories, and we built a model from this recognition model from this large labeled data set. Now, what we are going to do is that we are going to add new categories to our vocabulary. So we are going to try and recognize a new visual concept that we have not seen before. And to do that, what we don't want to do is to collect a large labeled data set again for this new concept. Instead, what we want is that we are going to use very few training examples for this novel category object. And then our job is to incorporate these novel classes so that now we can recognize both the original set of base classes and the new set of novel classes. So in other words, your base classes is your visual experience that you use to build your initial system. And then this system must be able to learn new visual concepts from very few training examples. So there are the two intuitions that I talked about correspond to two possible improvements we can make. One, we can change how we are learning how we are capturing this visual experience, how we are learning on these base classes to produce better feature representations, more invariant feature representations. And two, when we encounter these novel classes, we can figure out how we can hallucinate additional training examples that might help us to learn better. So let's first talk about better representations. Building invariant feature representations is like a mainstay of computer vision. It has been the main focus of a lot of work since when recognition started to be a problem that people are interested in. Our work is going to be to focus on convolutional networks, which is the main powerhouse of recognition work today. So this is what a convolutional network looks like. It has a bunch of these modules put together in a sequence to produce the final output. The last module is basically just a linear classifier that produces a score over all the classes. So I'm going to call this initial part of the network as the feature extractor, the function that takes an image in and produces an invariant representation. And the last part is the classifier. When I'm acquiring my visual experience on the base classes, I'll only change the feature extractor. I'll be changing both the feature extractor and the classifier. I'll basically be learning a good feature extractor. I'll be learning an invariant feature representation. But when I go into the world and encounter these novel classes for which we have very few training examples, I'm going to only change assume that the classifier feature representation is fixed and only change the classifier. I'm only going to retrain the final classifier based on my feature representation that I've already learned. So let's first see how when I'm learning the feature representation on my large set of base classes, when I'm acquiring my visual experience, how I can do better, how I can make sure that my feature representation will help me learn better when I encounter novel classes. So the standard convolutional network training objective is basically, some loss function of the weights and the feature extractor, and the loss function is some form of classification loss. Now what I want to do is I want to change this so that when I go out into the world and encounter these novel classes with very few training examples, I'm able to learn a good classifier from very few training examples for these novel classes. So I'm going to do this basically by simulating this kind of experiment, this kind of learning novel classes experiment on the base classes. So what I'm going to do is basically, while I'm training my convolutional network on this large data set containing thousands of classes with thousands of examples, I'm going to sample tiny training sets S from this large data set D. And now I'm going to say, well, given this tiny training set, I'm going to somehow have some low-shot learning loss that I'm yet to define that says, well, from this tiny training set S, I should be able to learn a good classifier. In particular, what I want to say is that on this tiny training set S, any classifier that I learn on this tiny training set should match a classifier that I learn on the large training set. So the classifier V that I'm training on this tiny training set should do as well as W, the classifier that is trained on the large training set. Now, training a classifier on a tiny training set corresponds to minimizing some loss function on the tiny training set. So what I want is that this tiny training set loss function, the minima of this, the solution to this minimization problem should lie close to the solution for a large data set training formulation. So this V star, this minimum of the classification problem on the small training set should match W, which is a classifier that I've trained on a large training set. This basically amounts to some difference between W and V star, some distance between W and V star. Question? So basically what I'm saying is that if I was to take this tiny training set and train a classifier on this tiny training set, it should match the classifier that I get from the large training set. Now, training a classifier on a tiny training set amounts to the optimum of some minimization function, some minimization of some classification objective. So basically, I want this V star to lie close to W, which is the classifier I'm training on the large training set. It turns out that this is somewhat of a hard problem to a hard thing to use as a loss function, because it involves, so this distance between W and V star, it involves this argmin. Now, it turns out that argmin is actually, so argmin is kind of a tricky function. If you want to train convolutional networks, you want the loss function to be differentiable so that you can backpropagate. Now, it turns out that argmin is differentiable, but it's really hard to differentiate. So we're going to punt on this. And instead, we basically came up with a proxy for this, a proxy loss function for this. In the interest of time, I will not go too deep into this proxy loss function. But the basic idea is that we basically use the fact that this function that we are minimizing is basically like a bowl, and we kind of want the bottom of this bowl to lie at some place. So the bottom of the bowl can be characterized by the slope of the bowl. But never mind all of that. Ultimately, what happens if you work out what the loss, what this proxy loss looks like, it takes the form of a weighted L2 regularization. So basically what this means is that if your feature activations, if you want to minimize this, or if you want to make it the case that it's learning from a small data set is the same as learning from a large data set, it ends up amounting to minimizing the L2 norm of the feature activations. How does that, why does that make sense? If your L2, there's two intuitions that you can think about. One intuition is that if you imagine your features have high L2 norm, it means they are very spread out in space. When they are spread out in space, if you just take a small number of them, if you have only a small number of them as your training set, it's likely that you end up with a very different decision boundary than if you have like the entire training set. Because they're just like so spread out, you get like these isolated points here and there, they might lead to very different decision boundaries. Another way to think about this is that if you have minimizing the L2 norm, you're minimizing this L2 norm while also minimizing some classification objective, which means that minimizing the L2 norm implies forcing the convolutional network to not put too much information into the feature vector. You're trying to reduce the amount of, because the feature vector is already, it's trying to do well on a classification task. If you minimize the feature norm, you're saying you have to do well on the classification task while you have this budget on how much information you can put into the feature vector. These are sort of two related intuitions. So because of this budget, what the convolutional network is forced to do is that it kind of prevents the convolutional network from encoding sort of confusing or useless features, or features that might slightly help the classification objective but actually might end up being very distracting when you have very few training examples. All of this is just sort of intuition. The basic idea is that adding an L2 regularization on the feature activations corresponds to some sort of a proxy loss that encourages classifiers trained on small datasets to match classifiers trained on large datasets. This is a visualization of the learned feature space from both the sort of the baseline representation where we only minimized the classification objective, and another representation where we minimized a combination of these two objectives. And as you can see, if you have this L2 constraint, the data points lie for each class lie closer together. They're more compact. And if you imagine just sampling a few training points from these class, then you can imagine that the decision boundary will still be fairly, will still stay fairly the same, whereas here the data points are a lot more spread out, so you're likely to end up with different decision boundaries. Yeah. So here we are actually, our goal is not, at this point we're talking about learning the feature representation. So you could imagine learning different feature representations, like an ensemble of feature representations. We haven't done that. We've been working with a single feature representation, which is kind of, in practice what you want to do, because you want to just store the feature representation, like Facebook, for example, will just want to store the feature representation for each image that's coming in. But you are right. I mean, it is possible that if you had an ensemble of feature representations, that will actually help. In fact, I'm pretty sure that will help few-shot learning. So this are some numbers. the red is the baseline. The blue and violet are like two variants of this kind of additional loss function, and it leads to a pretty big jump in performance when you actually have, this is basically an experiment where after I've trained on the base classes, I go into the world, I encounter novel classes with either 1, 2, 5, 10, or 20 examples per class. And as you can see, this is the accuracy. The accuracy, there's a significant jump in accuracy if you add this additional loss term when you're learning the representation. Okay, so that's, yeah.
This might be a stupid question, but the novel L2 loss that you're using, how is it different from L2 regularization?
It's not a stupid question because every reviewer asked us this. The L2 regularization we are doing is regularization of the feature activations, not of the weights. So that is basically the difference. It is exactly the same as L2 regularization, but it's a regularization of the activations and not the weights. This kind of activation has been done in like sparse coding literature, for example, but otherwise it's not been something that was explored. Yeah?
We are considering the case of new classes, does it perform bad or we treat that classes?
That's a great question. I don't have the results here, but it turns out it doesn't. Of course, if you crank up the L2 regularization, at some point it does start hurting the L2 regularization. But for a range of those hyperparameters, you see big gains on novel classes, but the base class performance stays the same. Yeah? No, so this is not the number of novel classes. So the number of novel classes is fixed. This is the number of examples that's available. Yeah.
Since you mentioned it's sparse coding, it seems like if you put L2 norm on feature representation, we are seeing representations that are non-sparse. Is there an intuition for that?
So actually, it turns out, so most of these convolutional networks, they end up with a ReLU, a rectified linear unit. So even L2 regularizations lead to sparse solutions. When you L2 regularize the feature activations, it still produces sparse solutions because these are ReLU. So if you like just keep decreasing the value, at some point they'll go below 0 and then they'll just be killed. We tried with L1 also. We tried L1, but L2 is much easier to optimize than L1. L1 is like very finicky when it comes to hyperparameter choices. Yeah. So it is, well, we learn it's an entire ConvNet, right? So it's basically like you realign all the feature representations from down to minimize the L2 regularization here. We could imagine doing L2 regularization of all the weights. We did try with weight decay, but that didn't seem to affect things very well. That didn't seem to, well, it didn't seem to change the baseline. It was basically the same performance as the baseline. Right. I don't have a strong, so one thing I should point out is that in spite of these being intuitions, we don't understand sort of what makes feature representations good for low shot learning very well. This is not something that's studied. People just, no one actually has experimented with, well, what happens to different feature representations and how they transfer when in the presence of low training examples. So these are intuitions that I'm giving. We started with some proxy loss function and we made some assumptions to get to the proxy loss function. So it's hard to say, for example, is it actually minimizing what the proxy that we actually tried for. Okay, so the second kind of direction is to hallucinate additional examples. So you have fixed a feature representation, you want to hallucinate additional examples. So the reason why this might be a good idea is that the visual world is very structured. Many different classes share the same kind of transformation. For example, all object classes will share a mode of variation that corresponds to, sort of camera pose changes, color variations, lighting variations, and so on. So it should be possible that from our experience on the base classes, we figure out that there are certain transformations that keep occurring. And if we can figure that out, we can use those transformations to actually create novel training examples. This kind of approach has interestingly not been tried that much. There's actually some very classic work from Eric where he did exactly that for digits and faces, where you basically have a dictionary of transformations and you try to figure out this dictionary of transformations based on an initial experience with some number of classes, and then you use this dictionary of transformations to hallucinate additional examples for every class. Unfortunately, one issue is that to go beyond digits and classes, when we move to 3D objects like this, it's really hard to model these transformations. It's not like a simple transformation. In image space, it requires understanding the 3D structure, and when we go beyond digits and classes, there is no closed form solution for what this transformation should be that we can just apply out of the box. There is some recent work from UCSD where they tried to do this if you have annotation. So if you have a bunch of data sets saying, okay, this is car A, this is car A from 30 degrees, this is car A from 60 degrees, and so on, then you can learn what this transformation looks like, how to transform like car at 0 degrees to car at 30 degrees. But the problem is, what happens if you don't have these annotations? So what we said was that, okay, we want to, so let's say we had given this one example of a novel category, and we want to have some dictionary of transformations that we'll apply to create additional examples for this category. But we don't have this dictionary, so instead what we are going to do is we are going to take kind of a non-parametric approach. So what we'll do is we'll take an example from one of the categories that we've seen and for which we have lots of examples. So let's say we get a stork. And for storks, we know that storks can appear both in this sitting perched position and in this flying position. And now what I can do is I can try to transfer this transformation from storks to herons to hallucinate this additional example. And another way of seeing this is that what we are actually doing is trying to complete an analogy. I'm trying to complete the analogy between sitting storks and flying storks, and sitting herons and flying herons. The way we did this was that, so we basically, to do this, what we need is something that actually can transfer this transformation in this way. So we need a model that can do this transfer. So we need to learn how to do this transfer. So to do this, what we did was we mined for these analogies among the base classes, among the categories for which we have lots of examples. So let's say we just have two base classes, a blue class and a red class. A blue class and a red class, and what we want is we want to find analogies that correspond to basically similar transformations, and we have no idea what the similar transformation is. We want to basically have large transformations. We don't want like slight changes in pose. That doesn't actually help us much. So what we did was we clustered these examples in each class into a few clusters, and then for every pair of clusters in one class, we looked for a pair in the other class which basically pointed in a similar direction, that were like close to parallel to each other. And if we found such a pair, we said that the clusters B1 and B2 were in an analogy with the clusters R1 and R2. We did all of this in feature space, so it's in some form of semantic space, in the learned feature space that we have. And if you look at sort of what these analogies look like, they're kind of like this. So you have changes in background, so birds in blue background versus birds in green background, whole oranges versus cut oranges, machines without people versus machines with people, and so on. So what we now have is a data set of these analogies. Each data point in this data set consists of a 4-tuple, 2 clusters of one class and 2 clusters of the other class. Or, well, 2 centroids in feature space of one class and 2 centroids in feature space of the other class. And given this data set, we can now train a model that takes the first 3 elements of the analogy and tries to reconstruct the 4th. So we have this analogy, R1 is to R2 is the same as B1 is to B2. It takes the R1, R2, and B1 as input and tries to reconstruct B2. And at test time, we get this novel category example. We basically just sample pairs of centroids from one of the categories we've seen and try to complete analogies. So we sample A1, A2 from a class A, and we try to feed A1, A2, and X to the generator to find out how to reconstruct, to complete the analogy. A1 is to A2 as X is to what. And whatever the generator produces, it's like a hallucinated example in feature space, and we just add these examples to the training set. Yeah?
How do you sample appropriate?
You got me. I tried a lot to sample intelligently. So, okay, just to make the question clear, right? When I showed you this nice picture, I mean, this was nice, right? I mean, like I have a sitting bird here and I'm using a sitting stock here. So clearly this is a nice transformation. So there's missing a piece where given a sitting stock, I find out this, sitting here and I find out the right thing to transfer from. I tried a lot to do this finding, but it turned out that just randomly sampling seemed to work best. Don't ask me why. Well, okay, so you can ask me why. So the thing is that this generator, in spite of the story, this generator is not really, it's not like a perfect generator. I haven't solved image generation. I haven't solved how to transform, learn how images transform. This is a fairly crappy generator. If you look at the feature vectors it generates, it's actually fairly noisy. It just has enough information to help us do the learning. So that's kind of one of the things that it's important to keep in mind. We are not interested in realistic hallucination. We are interested only in hallucination to the extent that it helps us to learn a good classifier. In terms of numbers, again, it improves a bit, improves significantly. So this red line is the baseline. This blue line is the baseline with this kind of hallucination. So when you have very few novel class examples, it helps quite a bit. Now, after we did this, actually, this approach, we were not very satisfied with this. This one reason was what I just told you, but it was also fairly fickle. So there were hyperparameter choices that were counterintuitive. We didn't understand why. For example, I told you that we clustered the examples in each class. Well, it turned out that sort of trivial details about how we did the clustering seemed to affect the performance a lot. So it was all somewhat dissatisfying. So we did get improvements, but it was not robust to a lot of these issues. So in one of the lessons from the past few years in computer vision is that, I mean, if you look back before deep learning, all the classic recognition models, they also had the same problem. They would be very fickle to hyperparameter choices and so on. And the solution was basically end-to-end learning. You have an end objective, you optimize for that objective, and basically everything is tuned for that particular objective. Now the question became, so how do we learn this kind of a hallucination in an end-to-end manner? And in fact, what does end-to-end even mean in the context of few-shot learning? So while we were doing all this work, there was a second class of approaches that was coming up in the machine learning community to the same problem, which was called meta-learning. So the idea of meta-learning is as follows. Meta-learning is basically end-to-end few-shot learning. So the idea is, okay, so what is our problem? Our problem is that we'll be given a small training set with very few training examples, and we need to produce a classifier. So we need a function that goes from small training sets to classifiers. And what do we do when you are a machine learning person and you want to create a function that goes from input to output? Well, you learn the function. So what we do is we make this a learnable function. So what we will do is we have this function h, some function that's learnable in some way that I'll get into right now. So h basically takes as input a training set and let's say a test image and produces a probability distribution over the labels for the test image. So this is a black box function. In traditional machine learning, this function will have two steps. First, it will run some learning algorithm A on the training set to produce a model. And then it will run this model on the test example to produce the probability distribution. What I'm going to do is I'm going to make this learnable by basically having a parameterized function. So h has some parameters w, and basically I'll train this through backpropagation. I'll get into what kind of functions we have here in a bit, but let's first see how we can train this function. So to train this function, I'll have my base classes with lots of training examples for thousands of categories. I will, again, sample tiny training sets out of this, and I'll sample a test set. And I'll feed the tiny training set and the test set into my function H to get a probability distribution. And then using the labels that I have for the test set, I'll have some loss on the probability distribution. And I'll basically backpropagate this loss to update these parameters W of this H, of this classification algorithm H. So this is kind of a weird idea, so it's perfectly fine if you have questions about this. Yeah?
Do the class, images in the test set, labels in the test set have intersection with labels in the training set? Yes, actually training and test set?
Yes, so this is, okay, so there are two training and testing. There's meta-learning training and sort of the final thing. So in this case, when you are training the meta-learner, you sample this training and the test set, and they have obviously intersection between the labels. That's why this learning algorithm can do anything about it. And when you finally, once you've trained this, you go out into the world, you'll just get a new training set, and you'll have to test on a new test set. Yeah?
So what is the difference between this and cross-validation? This test set is just like some validation set. You want to learn how to train the parameters.
That is a very good question. This is exactly like cross-validation, except, so usually in cross-validation, you basically have like 5 models that you're trying to see which one is better, and you just run it on this test set and see which one is better. Here, instead of doing that, you're basically doing gradient descent on the parameters of W. So you can imagine you're doing this cross-validation, but with like an sort of infinite set of models, essentially, parameterized by W. Okay. So this is a very popular approach for whatever reason. So there are at least 4 papers that I counted before we published our approach. So there is 3 or 4 more that came since on this general paradigm. And all these approaches basically differ on the form of this function H. I'm going to talk about the simplest one, which is easiest to talk about in this time, which is called prototypical networks. So in prototypical networks, so recall that what I want is a function H that takes a training set as input and a testing image and produces a distribution, probability distribution over labels. So what this does is it takes the training set, embeds all the training examples into a learned feature space. So the feature vector space phi is learned. It has some parameters W. And then it simply collapses each class into its mean. And basically, given a test example, it basically assigns it to the nearest class, or it basically gives a probability distribution based on distance to the means. So it's a very simple classification algorithm. It is differentiable because it's very simple classification algorithm. The only parameters to be learned are the feature extractor, and it is differentiable because you can, it's just computing means and taking distances to means. So it's all nice and kosher. And you can write it out in math if you feel you're not convinced that it's not differentiable. You can just write it out and convince yourself. So this is just the general space of meta-learning. So meta-learning is nice because it provides us an end-to-end way of framing this goal of low-shot learning. And now what we want is, well, we want to do this kind of hallucination. We want to hallucinate additional examples for the classifier. And we are going to take a hallucinator that looks like this. So this is a slightly different hallucinator. Now I don't have any analogies. I'm doing what the generative adversarial network people do, which is that you take you have your original seed example heron, and you want to hallucinate additional examples. Well, you feed it and some noise image to a neural network, and it produces a new image. We're also going to do this in feature space, not in image space, so that it's, just because it's easier to do this in feature space. Generating images is hard. And now what we want to do is basically we're going to update the meta-learning to include the hallucinator. So instead of directly feeding the training set into the classification algorithm H, I'll first sample a seed example, feed it to the generator to get additional hallucinated examples. So we get a bunch of hallucinated examples and feed the combined set to my classification algorithm. And when I'm backpropagating, I can backpropagate not only to these parameters W, but I can also backpropagate all the way to the generator and train the generator. So in terms of numbers, so this plot, unfortunately, I didn't have time to make cleaner plots, so I'm going to just sort of point you to some lines in this plot. So this one just shows the difference in accuracy between models with hallucination, without hallucination, and with hallucination. PN is prototypical networks. PMN is something that we introduced, which is basically prototypical networks with some ideas from another paper, so it's like a mix of two papers. But both of these are meta-learning algorithms. This shows the improvement with respect to the change in performance between the two. The solid line corresponds to the sort of curves I've been showing. We see very large gains of up to 7 percentage points for prototypical networks. The dotted line we discovered after the fact that the few-shot learning benchmark we were using, we could actually improve the performance of all methods by incorporating a novel class prior, like what is a prior that the class is going to be a novel. So you still see significant gains. That curve shows that the best approach that we had, which is sort of our prototypical matching networks with the hallucinator, with the trained hallucinator, significantly outperforms by a couple of percentage points prior work. Just our work works better. So these are the two papers. The first set of the first two ideas were in the ICCV paper we had, and then this one that I just talked about is in a CVPR submission. So okay, so I'll conclude now. We have about 5 minutes, so I'll just conclude now with some thoughts about where to go next. So the basic idea that at least the last two methods that I've been talking about is this idea that given a seed example, you want to hallucinate additional examples that you can just add to the training set, that you can create as data augmentation. But the approaches that I've been taking are a very sort of machine learning approach to it. Define a loss function and automatically produce the sort of the transformations. As a vision person, that's a bit unsatisfying. We know the kind of transformations, the factors of variation that a particular class has. We know that it corresponds to 3D camera variation. We know that it corresponds to lighting changes and color changes. We know that it corresponds to articulation. So the question that I think is worth asking is, can we learn how these transformations occur? Like, can we learn transformation functions for each of these kind of factors of variation without requiring carefully annotated training data, without requiring data about key points or camera viewpoints and things like that. So that is one direction. The other direction is I've been talking mostly about image classification. But image classification is like one dot in a vast space of like what understanding is. So I want to do, you may want not just classification, you may want object detection. Or you may want to estimate like the location of the bird's eye, the bird's legs, the tip of the wings, and so on. So the question is, how can we now talk about few-shot learning in the context of these problems? First, what does it mean to have less annotations when we talk about detection, segmentation, key point estimation? And second, well, now the challenge has become very, very different. So if I want to, for example, say, I'll just mark one key point location. Like I'll just mark the eye of one bird, and then you should go and mark the eyes of all the birds. Then that requires not just feature representations at the level of images, it requires feature representation at the level of pixels or at the level of fine-grained localization. So how do we use ideas that we've developed from segmentation, post-estimation, how do we extend that to the few-shot learning setting? So in conclusion, we can do recognition well now given enough training data, but for many, many applications, collecting this training data is very, very expensive, and we need to minimize the reliance on these large labeled data sets. And the way we need to do that is we need to incorporate more structure. We need to incorporate the structure of the visual world back into these models. That's it. Thank you.